Okay, good morning everybody. Today we'll be examining how objects fly through the air in Portal 2 under the influence of gravity and friction. In front of us, we can see that we have a setup. We have cubes stacked on top of hard light bridges. Each of these hard light bridges is holding the cube in place, and when I press this button right here, the bridges will disappear and the cubes will fall, at which point they will enter a momentum fling, coming out right there, and of course entering right here on the ground. During this test, we're going to be examining how far they fly, depending on how far they've fallen. We're going to be using graphs and some quantitative analysis to take a good hard look at what's actually going on in Portal 2. At the same time, we'll also be using console commands. They will be described in the comments section. It'll tell you how I'm doing, what I'm doing as this goes on. To start off, I'm going to go ahead and make my gun disappear and also freeze time. Time is now frozen, and when I press this button, we'll notice that the cubes are just floating in place. This is going to give me a chance to fly around the room and get a good view. Here we go. Okay, this looks pretty good. Let's go ahead, let time go, and see what happens. Okay, at this point, we've got all of our cubes in the air. We can see that they're frozen in place. We should notice that we have kind of a weird shape in front of us. It's kind of hard to describe. It's almost a parabola, but it's hooking back on itself at the bottom, and that is, of course, because the cubes that came out first, the ones at the bottom, also had the shortest distance to fall, and as such aren't going to go as far. Let's go ahead and continue watching in slow motion. We can see that they're hitting, each one landing progressively farther away, until we get to the end and it seems like they sort of stack up. And then let it go in full speed. Okay, that was pretty cool. Let's go ahead and take a look at the same event in a different angle. In full speed. From the ground. And again from the air. Okay, let's find out whether or not that stacking was real. We saw the last couple cubes pretty much land on top of each other. In this test, we have a same test chamber, but slightly larger. We can see that we have a few more cubes up top. It's a bigger drop with more cubes. Let's find out whether or not that stacking is a real thing. Okay, and our cubes are dropping. Let's slow them down and take a look at what's happening. We can see that they're spread out at first, each one landing a little bit farther than the last, but then at the end, they seem to be going in a straight line. We can see the last 4 or 5 cubes flying in basically the same pattern and landing in basically the same place. This is odd, this is strange, and not something I originally expected. Let's go ahead and do a little bit of math and figure out exactly what's going on here. To start off with, let's figure out how far the cube should go. Let's figure out a formula for that. Let's start with our equation for displacement. Our equation for displacement says that our change in x should be equal to our x velocity times time. Well, to find velocity, that's going to be our velocity of the cube when it reaches the portal. To find that, we'll be using conservation of energy and equating kinetic energy to potential energy. Doing so gives us a velocity is equal to the square root of 2 times g times h, and plugging into our original displacement equation, we find that delta x, or our change in x, is equal to the square root of 2 times g times h, all times t, or time. That gives us a graph that looks like so. We can predict how far our cube should go. This graph should look familiar because if you cancel out all the constants in our equation, we find that delta x is proportional to the square root of h, and that is exactly the type of graph we have here, a square root graph. Okay, now if we were to actually go through, count panels, go one by one for each cube and figure out exactly how far they actually went, we get this graph. We can see our red line, that's going to be our data. Our red line is slightly different than what we expected. We can see that first of all it's a little bit lower than our expected velocity, or our expected displacement. That is to be expected because these cubes are affected by friction and slowed down. We also see the separation between the blue and red graph increases as our initial height increases. That's because faster cubes should be slowed down more, should be affected by friction more. So we should expect a separation to increase as initial height increases. However, we're not expecting our data to level out. We can see that right around 7 or so panels, our data levels out and our change in x doesn't change at all. All the cubes are landing in the same place. That is a weird, strange feature of Portal 2. Our portals tend to slow down objects moving through them. There is some type of speed limit or terminal velocity for objects moving through the portals, and it seems like we found it right here. Okay, that's weird, that's strange. It's a quirk of the game, but still very interesting in a physics, from a physics mindset, and another cool way of exploring the game. That's going to be it for today, guys. If you have any questions, comments, or concerns, please add them to physicswithportals.com or go ahead and comment on the YouTube video. Take care.